Okay, so if you remember, we in the previous lecture we started with the new topic regarding neural networks. So in contrast to linear models, as we saw in the first part of the, let's say, the first module of the lecture, neural networks are used because we aim to describe also and especially nonlinear processes. So as we remarked in the previous part, of course, system identification methods were limited to linear models. So as an extension, we need to consider alternative procedures for the modeling, for the description of nonlinear processes. So one of these, one of the methods that are now especially exploited for this task are represented by neural networks. And in the previous lecture, we introduced this argument, and in particular, artificial neural networks were inspired by the biological evidence. So we saw also an example of a biological neuron. And so we introduced this general structure. The structure is very simple because an artificial neuron is described as a nonlinear function. Normally is a static nonlinear function whose arguments are the inputs of the neuron. So in general, we have p inputs. Normally they represent what we call the patterns used by the network, and normally the output is a scalar, because the output of the activation function here, sigma of z, is a scalar. And we saw also different examples of activation functions. The most used one are represented by, at least in our investigations, we are considering what we call the projection function. So in general, is a function, are functions which depend on the summation of all the inputs of the neurons. And of course, there is another family of neural networks which are represented by the radial basis function neural networks. So we are not going to consider them in this course, but they represent an alternative approach because on one side their structure is very simple. They have, as we will see in the next slides, they have only one layer, and the procedure for that is used for estimating the weights of the neurons is based on a very simple analytical relation. So it will be very different from the mathematical procedure that is normally exploited in neural networks, because it requires a numerical minimization of a cost function. So it's something quite different, but we are in our considerations or in our applications we are introducing. So the artificial neural networks of this type. So normally the activation function is represented by a nonlinear function. The most used is the sigmoidal or tangent hyperbolic functions. As normally these two functions are used in the input and hidden layer, while for the output layer we are using a linear activation function. So this was the first part of the lecture we considered the last time. So today we will consider the case of the simplest neural networks and their approximation properties, just a very brief insight into these structures. This is the example of an interconnected neural network. So in the picture here on the left, we have a multi-layer artificial neural network. As you can see, all the neurons are fully connected. So it means that the input of the one neuron receives the inputs from the previous layer. And as you can see here, for example, in the input layer and in the hidden layer, you see that, for example, this neuron, I'm hiding here. So, for example, this neuron here in red received the information provided by this neuron, this neuron, this neuron, and this neuron. So, this means that when we say that they are fully connected, and the same, the output of a neuron goes to every neuron in the next layer. So normally we are considering this structure of neural networks. They are called M with the acronym MLP, so multi-layer perceptron, because according to the literature, a neuron, a simple linear neuron was called as perceptron. So it's why they are regarded as multi-layer perceptron, MLP. Artificial, you can also drop the letter A, because we are saying MLP neural network without artificial, because it's something that is well known. We have another family of neural networks that are called, normally considered for dynamic applications, and in this case we have that the output of one neuron is sent back to the input of the neuron. So the structure is different, because according to a simple multi-layer structure, there is no feedback. There is no explicit feedback. So the direction, the flow of the information goes from the input I to the output O, and the behavior is static. So it means that the output is a static function of the signals of the input. In this case, on the right side, we have that the first difference is that we have just one level, one layer. So in this case, we have one layer with 4 neurons. Every neuron has 4 inputs, and the inputs come from the feedback of the output of these neurons. So this is why it's called single layer recurrent artificial neural network. So this is particular structure of neural networks. We are not considering them for our practical purpose, because it's easier to train a multi-layer perceptor neural network rather than a single layer recurrent. So we are not including them in our considerations. And a few more details, or an example here. We have, in this case, in order to simplify our considerations, you can see here that we have one input layer. Well, in this case, the input layer is just like a hub that connects or collects the inputs. So again, we have P P stands again for patterns. So we have P inputs. Every input, as you can see here, can feed the neurons in the hidden layer, and also in order to not to have a too complicated structure, the connections are not completely shown here, but every connection, so from one input to the neuron, is weighted by a weight, which is called W, with the subscript with, in this case, 1, 1, which means that connects the first neuron of the input layer to the first neuron of the hidden layer, and we have this upper script H, which means that this weight refers to the hidden layer here. And then we have, in this case, the output layer. So the output layer, again, using the same notation, we have W, O, because it's the upper script O, because it refers to the output layer, and again with the subscript, which refers the number of the neuron in the hidden layer with respect to the number of the neuron in the output layer. And then we have also another characteristic that, as you can see here, the hidden layer uses the sigmoidal or hyperbolic tangent activation function here in red, while the output neurons are using linear activation function. So also normally this is the very common structure for these neural networks. And in this case, as you can see here, so we can select, it is not a constraint, so we can consider an arbitrary number of neurons in the hidden layer, and we have only this constraint that the number of neurons in the output layer is equal to the number of outputs. So this is the only constraint in feedforward neural networks. And according to the mathematical relations, so we have the activation function of the hidden layer neuron with the number J. So we have that the output of the neuron J is computed as a summation of the inputs to this neuron J coming from the, as you can see here again, the subscript. So the input goes from the previous neuron I to the, or input I, to the neuron J. H again refers to is the weight referring to the one neuron in the hidden layer, and this is the constant, is a bias, it's called bias, B of the neuron J in the hidden layer. And the output of the hidden layer is very simply the result of this activation function. So again, sigma is normally, again, is a sigmoidal or hyperbolic tangent. The output, we have the output in the same way. So according to this structure, the output of the output layer neuron L, in this case, has the same structure of this one, but only is that the only difference is that the activation function is linear. So it means that the output of the neural network is simply the summation of the inputs to the neuron, output neuron, multiplied by the weights and the input plus a bias Bj. There is so, by considering a very simple example of a network, as in this case, with two layers in order to simplify the computation of the overall transfer function from the input to the output, we can see here, this is the activation. So in fact, since we have just two inputs, as in this case, in order again to simplify two neurons. So we have that here the function of the activation function is described by two straight lines with the weights of the two neurons, and the transformation through the hyperbolic tangent, as you can see here, is obtained as a composition of these two functions, because this is this corresponds to the output of the two neurons provided by this equation, and then the output is obtained as a summation of the neurons in the output. So as you can see here, the output is given by the function in red, as you can see here in red, which is obtained as a composition of the two outputs of the two neurons. So this is an example of the approximation function of this neural network. And in order to provide also a practical way for computing these weights, it's better to describe these equations, this single equation, in a compact form, which is represented normally by vectors and matrices, and in particular, so we can write the vector of the output z obtained as a composition of the so z, as you remember, is the input of the neural network of a neuron, and can be written as with xp, which contains all the inputs, so in compact form by using a matrix or a vector notation, and a vector containing the weights. So this notation is very simple, because you can simply derive the output to the neuron, and then the transformation of the output through the activation function of this neuron v, with the vector which contains all the outputs of the hidden layer, and then the output, the global output of the network, is computed as with v. Is a vector containing the outputs of the previous layer multiplied by the weights of the output layer. Of course, xb here is x with a row with a column of all ones, because it means that you are including, when in order to simplify the notation, normally the bias b, which is an unknown in the neural network, is included as a weighting parameter multiplied by a constant input, which is 1. So this is a normal way for transforming an affine function as a linear relation. It's simpler to consider this formulation. So we can include in the inputs the one which corresponds to the constant input which multiplies the bias. In this way, again, the bias becomes a weight which is included in the weighting matrices WH and WO. So it's very is very useful because we can obtain a very simple formulation or very compact formula for this feedforward neural network. As you can see here, the output is the result of the transformation through the hidden layer and the output layer. So as you can see here, it's very simple to represent the function of the neural network. Let's see some approximation properties of the neural networks, of course, without any demonstration. So we are considering them as properties. So a quite recent result is that a feedforward neural network with at least one hidden layer can approximate, this is a very important result, because it can approximate any continuous nonlinear function with a number of inputs p to a number of outputs n. So also the number of inputs and outputs of this nonlinear function is arbitrary. Of course, is a continuous static. So again, we have the constraint that, or the condition that the output is a static function of the inputs with an arbitrary degree of accuracy. So it's very important because you can reduce the approximation error by increasing the number of hidden neurons. Of course, this, well, is not really a theorem because it's just stating that when you increase or given a sufficient number of new hidden neurons, you can represent or approximate any continuous nonlinear function with arbitrary accuracy. This is a very important result. Of course, this theorem, let's say, of course, is not really a theorem, but this condition says that provided a sufficient number, so it doesn't say how many neurons you need to have this approximation. So it means that normally you perform a trial and error procedure in order to find, of course, depending on your on the error that you want to obtain, the approximation error. We have another important result, even more recent, so given by Baron. So a feedforward neural network with one hidden layer and sigmoidal activation function can achieve an integrated squared error. So it gives the order of the error, which depends on the number of hidden neurons. So this is another important result because it says also that here it does not depend on the dimension of the input space. So it doesn't care about the number of inputs, only it depends only on the number of hidden neurons. So it means that if you increase the number of hidden neurons, you are reducing the error, the achievable error, or the order, let's say, is the order of. So normally the order, I don't know if you are familiar with this index, the order means the terms that can be neglected after the approximation. So it gives you like the level of your approximation, and it depends on the inverse of the number of neurons or in the hidden layer. And we have another important result, which is used as a comparison, because we have instead another result that if you consider, instead of neural networks, if you consider basis function expansion, for example, polynomial. So if you are using, for example, a polynomial approximation, this is of course, you can also consider a trigonometric expansion, but is normally more common to find a polynomial approximation with h terms. And of course, the parameters are a linear combination. So as you can see here, the approximation order depends on 1 divided by h squared divided by the number of inputs. So for the case of polynomials approximation, there is also another parameter which depends on the number of inputs. So it represents a limitation, because here it doesn't care about the number of inputs, but here it takes into account how many inputs you are including. So we have the next slide, an example, which means that, for example, for the case of two variables, so you have two inputs, you have that the polynomial has the same order of a neural network. So there is no difference, of course, for quite simple structures. So with a limited number of inputs, the approximation properties are the same. So there is no advantage with respect to a polynomial. But when the number of inputs increases, for example, we have a function of 10 variables, which is quite common in neural networks, and a number of 21 neurons. You can see here that a polynomial approximation can lead to an approximation, an error of order 0.5, here about 0.5, and a neural network with the same with the same structure. So it means that with 21 neurons, the error that can be achieved with the neural network is 1 order of magnitude lower than a polynomial. So this is an advantage, because with the same complexity, the approximation error is much smaller than the one achievable with the polynomial. This is an important result. And so this is a comparison if you consider the same structure. But if you want to obtain the same accuracy of a neural network, for example, if you want here to obtain the same accuracy, the neural network equal to a polynomial approximation, so you can replace it, and you can see that the number of parameters, or the h, in your polynomial, instead of 21, needs to be 4 multiplied by 10 up to 6. So it means that when the number of inputs increases, the polynomial solution is much more complicated than a neural network. So is in terms of, for example, computational complexity or storage in terms of memory. So it's very important, this practical result. So let's discuss that some properties of the neural networks. So these considerations lead to some to the comments. So a neural network with one layer can achieve a lower approximation error that can be very small, independently of the dimensionality of the input space. So this is very important. So these results lead to the conclusion that neural networks are suitable for problems with high dimensional inputs, like we will see later, like images. Normally, neural networks are applied for image processing. Of course, according to the previous results, let's say the results that we saw in the previous slides said that we have some limits, but it doesn't mean that it's always possible to have or to go near to the theoretical limit. Another conclusion is that by adding more neurons every layer, it doesn't reduce the approximation error, because we will see later that it depends on you need to validate your model, as for the case of the linear system identification. And another result is that normally one layer is not optimal. So normally, well, if for our applications, it means for signal processing, normally we are using a number of layers equal to 3. So normally 3 is the optimal number of layers, at least for signal processing. But when you go, for example, or you move to the framework of deep learning, for those of you who are familiar with this term, so deep learning. So normally with deep learning, we have much more layers. So it's normal to have, I don't know, more than 10, 15, 20. In fact, I included here some just remarks. I don't want to give you too many details on deep learning, but because it's a topic that is very important in the last year. It became very important, especially, let's say, in the last, as far as I know, the last, let's say, 7-8 years. Especially because it was included in the when you work with image processing. So we now is very common to include this framework of the deep learning with image processing. So normally image processing is used in connection with deep learning, and in fact, as you can see here, this is just a graphical picture or a graphical interpretation that when you want, especially you want to reduce the dimensionality of your problem. So in fact, for many problems defined in a very high dimensional space, which is represented here as a collection of many images, the data are transformed into a lower dimensional manifold, which is represented here. And as you can see here, we have a lattice of, so a lower dimensionality space, and is something that is the, let's say, is the transfer function performed by a deep neural network. So normally there are these three categories. Normally we are we are here. So in classical control, as in our framework, normally you have the input, and we have a mapping which normally is obtained by, for example, by analytical relations, so by the knowledge of the problem, or with a model-based approach, we are able to design the desired output with respect to the provided input. And if you move here to the now the novel application of machine learning, you have the input. You can consider or introduce some features, and the novelty when you are considering the machine learning, that some mapping can be learned by the data in order to obtain the your output. This is the classical machine learning. So when you, for example, you are considering a multi-layer perceptron neural network. So when, for example, you have a limited number of layers. In the framework of the deep learning, which is normally referred to as DL, so with DL, in contrast, here is referred to as shallow learning, because it's shallow. It means it's superficial. It's something very so shallow. Shallow. The term shallow refers to the limited number of layers. No more. Normally, no more than 3. Here, as you can see here, so the objective of every layer is to extract or to learn features. So it's why in deep learning we are introducing, in some cases, many layers of one network, but it's something that normally we are not considering here. So we are moving from the classical control. So due to the classical control helped by machine learning and limited to the use of multi-layer perceptron with a limited number of neurons. So it was just a very brief introduction to deep learning, just to discuss with you some, not to enter into the details of deep learning, because I'm sure that you have already attended some other courses on deep learning. So let's examine the problem of the training of a neural network. So training means that the procedure, or is the mathematical way for estimating your parameters, your weights, which is the final objective of the training. So when you are training a network, the training of a network means that you want to estimate the unknowns, which are represented by the weights of a neural network. So according to the neural network training problem, the goal is to find a weighting vector W. So W contains all the possible weights by minimizing a cost function, or it's called cost function or loss function, because it's a function of unsuitable parameters. Normally is defined as a function J, which is not really, well, a function, but is an operator, because it applies to a function which depends here, as you notice, it depends on the inputs X and the weights. So for all the inputs X, is certain here, as you notice, that is especially unseen. Unseen means that you train your neural network using some inputs, and your objective, your final objective, of course, because normally the neural network is trained, when it's trained using the input X, it means that these networks work properly when they are examining the inputs X or the data from where they have learned. But your objective is that the neural networks must show that the network was able to give also the right or the correct result also when you apply some inputs that were not considered during the training. This is a very important property which is called generalization. So when we speak about generalization, it means that the neural network should work properly also when some unknown or some unseen inputs are used. So this is an important feature of our network. And in fact, we normally speak about or is referred as supervised. So supervised because normally you apply to a network the input which are called pattern, and for each pattern you know the target. So you know that the network fed by this pattern should answer with the desired target, which is called T. So it's normal that you compare in order to optimize your training. So in order to optimize the approximation properties of your neural network, it's normal that you want to minimize the difference between the target. So the target means what you want to obtain, and the effective output, the actual output of your network, which is called, it can be called O. So O stands for example, the output of your neural network with respect to the target, or also denoted as target. So what you would like to achieve. And of course, because this difference should be minimized with respect all possible examples, so all over your data, normally this difference is square, because of course you need to consider all possible contribution to a cost function, and this contribution needs to be positive, because if you are guaranteed that if you are minimizing, in order to minimize your cost function, you need to minimize all possible contribution for each example. This is the meaning of this supervised learning. So we can define, of course, I don't want to enter or provide too many details on the general algorithm, but normally the procedure for obtaining your parameters of your neural network, which are represented by this vector of weights W, you must use a numerical algorithm, because the function that you want to optimize, to minimize, is a highly nonlinear function. So a closed form solution or an analytical solution cannot be used. So it's why normally you exploit numerical minimization or optimization. So normally the procedure starts by initializing your weights to a random values, and you perform an iterative procedure which starts by what we call the forward pass. So forward pass refers to the task of applying the input and then calculate or compute the neural network output. So y equal to f of x, which is the input, depending on the actual weights w. Then you calculate the cost function g, which depends, of course, on the output provided by the neural network and the target. And so you compute this cost. And then we introduce also a phase which is called backward pass. So backward pass refers to the way to calculate the gradient of the cost function with respect to the weights, because in order, if you want to minimize, as in mathematics, in order to derive or to find the minimum of a cost function of any analytical function, normally you compute the gradient or the first derivative of this function. So in the same way, we compute the gradient. The gradient, because can be a multivariable function, so we compute the gradient of this cost function, and of course is a vector because it's a multivariable problem, because you need to minimize this cost function with respect to all possible unknowns, which are represented, as you can see here, by each of the weights in your vector W, capital W. And then you perform, as a third step, the optimization phase, which means that you update your weights based on the gradient in order to, let's say, normally it's said that you move the weights in the direction that leads to a reduction of your cost function. So it's why we will see in the next slide the procedure which is based on a gradient descent approach, because you are moving into the direction which leads to the minimum of your gradient. So, and then we have this picture which represent a graphical, let's say, representation of what we call the supervised learning. Supervised because it means that you are comparing, so it's why it's defined supervised, because you are comparing the actual output here with respect to the output provided by the neural network. So you are comparing the desired output, which is the output of your system, and which is also the target T, or desired, so which with the output Y of your neural network. So you are, according to the error, there is here this arrow, which means that you are changing the parameters such that this error here is minimized. So this is the procedure of the supervised learning. There are other types of other methodologies which are called unsupervised, for example, or also we have the case of the reinforcement learning. There are some more recent procedures. I'm going a little bit into the detail of the, in order to show you the way of computing the training or performing the training of a neural network. So you see here the phase one, which is the feedforward computation. So it means that from the inputs, you proceed through the hidden layer to the output. Again, by using the scheme of a very simple neural network. So from the hidden layer, and the inputs here, x of b, because if you remember, x of b is x, so the inputs, which includes also, if you remember, the one which stand for the bias. And so this z is propagated to the activation function sigma, and then v is the output of the hidden layer, goes from here to v, as in this case, through v, as vb goes through the output layer, and then you can compute from the input x. Here you propagate the information, as is, you can propagate, you can see here, you propagate through your network, and you move to the output. This is what we call feed-forward computation. So in fact, this kind of neural networks are defined also as feed-forward multi-layer perceptron neural networks, because there is this feed-forward phase. Then we have the weight adaptation. So when we have at the output, we have the output y, we can compute as a difference. So we compare the output of the network with respect to the target. So this is the objective of what we call supervised learning. So we compute the error, and we try to minimize. So once we compute the error, we are trying to modify, to adjust the weights such that the following cost function, the following function, is minimized. So with respect to this vector w, which contains both the weights in the hidden layer and in the output layer. So we are examining with this picture. So we have for example, for the case of the output layer, you can see here the single neuron. So the output of the single neuron here is its weights, which weights the inputs to the neuron are summed up here, and then you have the comparison with respect to the target. So the actual output of the neural network is compared with the target. So this is the example of the supervised learning, and then we can compute the cost function. The cost function has this form where e is equal to t minus y, y is the summation of everything, and here you can see that in order to find the dependence of or the link between the cost function and the error, you need to compute the first derivative here of g with respect to w, but g depends on a, so it's a function of a function. So normally you need to compute j of as a function of e, but e depends on y, so you need to derive the partial, of course, derivative of e with respect to y, and then y here, as you can see here, is y, which depends on w, and finally you can, as you can see here, you can you can show the relation between the derivative of your gradient with respect to the output, as you can see here, of the neurons and the error here, e. Let's go ahead. And then by moving backward, so for the output layer, as you can see here, so we move from the output layer to the hidden layer. So it's why this procedure is called is defined as backward, because from the output we are moving towards the input of the neural network, instead of, which is opposite, is the opposite of the case of the feed forward, because in the feed forward phase we are moving from the input to the output. In the backward phase we are computing the derivatives of the cost function with respect to the weights by moving from the output to the input. So it's why for computing, as you can see here, the derivative of the cost function with respect to the weights of the hidden layer, so the previous layer, we need to perform this computation, and we can see here that we can understand another important result is that the as you can see, the derivative of the cost function is another important point, depends on, as you can see here, the derivative of your activation function. Of course, the derivative depends on the input, so there are different factors. So depends on the input, on the derivative of the activation function, and then on a contribution of the error from the previous neurons, and the weights of the weights of the output layer. And as you can see here, so the derivative of your cost function with respect to v, which v means is the output of the hidden layer, is this term, so which depends on the error and the weights of the output layer. The second term here, so the output with respect to the input to the neuron is affecting the output with the first derivative of the activation function, which is a very important observation. And then you have the last term, which says that the variation of the input of your hidden layer depends on the input that you are providing. So also the training of the neural network depends on the input that you are applying to the network. So let's examine, as for in the previous case, an example of two layers, as you can see here. Two layers with two neurons, and one single output. So you have, in this example, one neuron in the output layer, and then we have, for example, one hidden layer H2, another hidden layer H1, and then the input layer. And as you can see here, we have an effect, or a cross effect, between the neurons in the two layers. So they are affecting also the output depending on the cross relation between the different neurons. And in fact, as you can see here, the derivative of the cost function with respect to the weight here depends not only on the relation of the, excuse me, okay. It depends not only on the relation, on the direct relation between the neuron, the first neuron in the second layer, to the first neuron on the first layer, but also on the second neuron on the second layer to the first layer. So we have a cross coupling between the neurons. Well, considering the cost function, there are different formulations for the cost functions, and they depends on the task you want to solve or to implement. Normally, there are three kinds of tasks that a neural network can perform. The first one is the classification task, when you want, for example, to recognize objects. The second one, and is not our case because we are not classifying images or objects. The second one is the regression. So this one is the task that we are interested in, because normally we are considering regressions of our signals. So is the typical application of signal processing, or we can consider also regularization. So regularization means that you are including also some constraints on the variation, in the variation of your weights. This is an important also application. It is not really considered in our applications, but it can be an interesting topic in the general context of neural network. So there are two main criteria when you are performing you are considering or you are working with the cost function. So normally, the minimum of the cost function which is indicated as the value of the weights, which minimizes the cost function with respect to the argument of the loss function, should correspond to desired behavior. Normally, we are considering the square of the difference between the output and the target. It means that we are minimizing our error as an average sense, which is normally when you are performing the training of a neural network, we are considering this aspect. But there can be also not only this kind of metric here, which is the square, but we can consider also the one norm that can be, for example, in the case of a scalar, is the absolute value, which corresponds to not really an average, but what we call a median, which is quite close to the mean value, and it depends on the task that you also depend on the values of the error. Another important point is that the error gradient should be informative. So it means that when you are computing the minimum of your cost function, because as we saw in the previous relations, that the minimization or the gradient depends also on the values of the error. So the error should contain informative or detailed information regarding the signals. So it's something that should be carefully considered while you are performing the minimization of your cost function. So I think that we can just stop here for a short break, or let's say 10-15 minutes, because I think we have already had about 1 hour of lecture. So if you agree, we can stop here and continue later to have discuss some more details on the optimization of our cost